Swayam Prabha. Digital India. Educated India.
Welcome to Module 6, Lecture 3. If you recall, we discussed about factors affecting strength of concrete in the last two lectures of this module, and we also said that it is the test condition that has a role on the value or on the estimated strength that we get, estimated cube strength or cylinder strength that we get from our tests. So, what are the factors related to test condition that affects these test results are is what we are going to look at today, right. So, it is essentially we are looking at what are the factors and how do they factors, what are the factors and how do they affect the strength, the test condition, test related factors that affect the strength, statutory factors, those will be affecting the strength. So, general outline, compressive strength, the factors which affect the compressive strengths are end condition and capping of the sample or the sample of the specimen that I take, size and shape and aspect ratio of the specimen, rate of loading, and then we will look into some of these aspects related to tensile testing, some of the aspects related to tensile strength testing. So, compressive test, compressive strength, test for compressive strength actually what we do, let us take a cube and we apply load from top and bottom to a machine, testing machine, where this load is applied through hydraulic system, and we can also control the rate of loading, etcetera, etcetera. So, we apply load like this and we define the strength as P max by A. That is a simple way of doing that, and test condition induces variation in results. That is what we are going to see. Of course, therefore, I must have a standard test condition. Now, if you recall some time earlier we talked about that the cube strength that you get actually is not really a measure of the strength that you get in the structure, because several factors would be affecting the strength in the structure as well as that obtained from the cube test, and they are not same. The factors, values of those factors or levels of those factors are not same, but then it gives us a relative measure. It gives us a relative measure of the materials that has gone in concrete making. Since the test condition affects my strength, I must standardize this test condition and use the same test condition for all the cubes, so that I can only compare the materials. So, standard test condition is given in codes. In Indian scenario, it is given in IS 516, originally framed in 1959 or so, but then it has been reaffirmed last possibly sometime in 2009 or so, right. So, it remains same, still remains same. So, what we do, we apply load from the top, uniformly distributed load on the cube surface, and bottom there is an uniformly distributed, we assume that there is an uniformly distributed reaction from the machine frame or machine plate as we call it. We apply the load also through the machine plate, and as we apply, the reaction comes from the bottom and the concrete cube is crushed under those two loads, all right. So, that is how we test cube, but we can test a part of a beam as well, we can test the part of a beam as well, right. We can test the part of a beam as well. So, for example, this is the whole beam, this is the whole beam, this is the whole beam, this is a beam, part of a beam, after doing flexural strength on the test for flexural strength on a beam. We will discuss this test for flexural strength sometime later. After doing that test, the remaining portion, unbroken portion, actually I can test under compression. So, the load is applied through this and bottom plate is here. So, applied through the top plate, and then as we press it goes down and I get some results. Remember, this results is not the same thing. IS 516 gives test on portion of a beam is not same as the cube, is not same as a, and these two things are not same, they are not same. They give you some, this gives you some strength, the other one gives you some other strength. But anyway, that is good enough for our purpose, because we are relatively comparing. So, compare these results with only the beam results, compare cube strength result with only the cube strength result. Now, this is not so popular, while cube is very popular. Cube is most popular and commonly used. This is rarely used actually. Now, end condition in capping. End of test specimen shall be truly plain, first of all, this should be truly plain. This is what we talked of. Now, this should be truly plain actually. This should be truly plain. This portion should be truly plain. This should be truly plain. Otherwise, the undulation, the contact area would reduce and there will be stress concentration, So, effective contact area will reduce and apparent strength will reduce. So, therefore, this must be, first thing is it must be plain. And to do that, what we do? What we do is we cast surface cast against steel mold are smooth, and therefore, it does not require any treatment. I will talk about capping a little bit later on, but it does not require any treatment. This is very smooth, and I put that below the loading plates, what we call loading platens. So, I put this one, this top portion, this portion is this portion, this portion I am talking of. It is that one which was in contact with the steel mold during casting and not exposed to air. So, this will remain by and large plain if my molds are standardized and properly made within tolerances, then this will remain plain. While we can do this for cubes, well, cylinder actually you cast in this manner, cylinder you cast like this. So, this surface is always exposed. So, this surface is always exposed, this surface is always exposed, this surface is exposed. So, we apply load however through this. So, anyway cylinder scenario we can't apply, but we have to see that it is sufficiently smooth, there is no variation, right. Now, that is as far as cubes and cylinders, largely cubes are concerned. But if you cut a core from actual structure, sometime we do that, we will not be, right now we will not be discussing this, but sometime we cut a core from the, cut a core and from the structure. So, this is a core actually, this is a core cut, cut core from the structure, which we have seen in the beginning, first lecture, if you remember, I actually showed you a core. So, we cut a core from the structure, and this core sometime may have rough surfaces, and or length may not be sufficient. You have to have a specified length depending upon the diameter d. So, L by d. So, there is a minimum L by d which is 1, but supposing I have got slightly less, then I might do some sort of a capping here. That means, put some materials and do capping, So, if you do this kind of capping, you will see that the results in variation in the strength. So, that is what we are saying. So, end capping results in strength variation, right. End capping results in strength variation. Now, this variation or the difference that we get is attributed to lateral expansion of capping material and concrete, relative is both will be the capping material can be expanding. So, what you are doing when you are applying load like this on this one, you are applying load like this, material here would be actually expanding, So, if you put a capping material here, this will also expand and concrete will also expand. So, it is related to this sort of expansion of this capping material and concrete. Let us see how it is. So, we will see that right now, we will see that right now, how it affects. Supposing I put different capping material, let us say first is this is alumina cement, first one is the alumina cement, this one is the alumina cement. So, I have made actually cubes or cylinder like this, and I am using different capping material here. They might be this might be rough, this may not have been smooth, etc. I am using different or whichever way, this is a result of experimental results. So, I am actually doing some capping and capping here, put this capping, and first material that I am talking of is alumina cement. So, this is alumina cement, and second one is gypsum plaster, third one is another gypsum plaster, fourth one is sulfur with filler, sulfur concrete with some filler, sulfur actually colloidal sulfur, yellow sulfur you might have seen, it actually melts. So, you put some aggregate into it, some filler, then it becomes almost concrete when it solidifies. So, the sulfur concrete. So, I can put some sulfur, plaster of Paris, calcium sulphate 2H2O that we know, and POP plaster of Paris with ordinary Portland cement. So, plaster of Paris is this, ordinary Portland cement is here, 6 is sulfur, 5 was same as sulfur with filler and is pure sulfur, 6 is right. So, you see if you have different capping materials, same cubes or same cylinder, if you look at relative strength, if I assume that high alumina cement gives me 100% strength, for strong concrete it goes on reducing with the capping material, and for weak concrete the effect is somewhat less, in fact you find slight increase. Well, this is a qualitative statement, I am not doing quantitative statement. So, what we observe is that there is a variation and it depends upon the type of capping that you are using. So, end capping has an effect on end condition. Normally, if you do not have a capping, the machine plates are straight away coming in contact with, top and bottom, which are usually steel. So, you have steel plates, they come in contact with the specimen itself, I mean the sample specimen itself, all right. So, specimen itself, so that comes in specimen itself, all right, not sample, specimen, because sample would be a couple of specimen would make sample. So, it specimen from the sample actually. So, specimen Q specimen itself, all right. So, this is what is happening, machine plates coming, and if you put depending upon strong or weak concrete, the F factor will depend. So, you see it depends both on the strength of the concrete, the quality of the concrete, as well as the effect of the capping material is a function of the strength of concrete again. It is a kind of nonlinear situation. So, that is what it is, and therefore, this is an important issue. So, end condition and capping, this is an important issue. Now, what is the mechanism? Let us see if I have some diagram, some diagram right now I do not have perhaps. So, no problem. So, what okay, yeah, but explanation is there. Let me use my own diagram, right. Let me use my own diagram. Okay, the observation is, I mean, or let us first use this my diagram and then I will come back to. Now, this is your cube, you are applying load like this, and we have discussed that my material will have a tendency under this compressive uniaxial compressive situation, it will have a tendency to move along this direction as well as along this two transverse direction. Now, if tries to move along this direction, that means it finally the failure is because of tension. Then the movement is important, movement of this material along this direction is important. Now, this point, the movement of the material is restricted by the friction between the machine plate and the specimen. So, there is a kind of a force acting like this, frictional force, which will not allow this movement. Similarly, here this is a kind of a frictional force which will not allow it to move along this direction. So, there is a surface, but then surface material is in contact with the just bottom next layer of concrete. So, if there is a force acting and it is trying to contract, let us say trying to expand, it would also try to take the material below, but if there is a force opposing this, this also will be opposed somewhat, but it would gradually get reduced, get reduced. There is some sort of opposition to the movement here also, but gradually it will get reduced. In other words, your this forces, resisting forces, I mean it would get reduced somewhat. So, you do not have really purely uniaxial situation, you have a situation where there is some sort of a force acting onto the specimen depending upon depending upon the type of specimen or L by D up to some height, this there is a force acting like this also, some height force acting like this also, this will depend upon this is your L and this is your D, if I may say this is the D is the dimension of the cube. So, if it is D and D, then there is somewhat overlap is there, we will come to that just now. So, you see there is a opposing force or to the movement, horizontal movement or transverse movement, this is opposing force to transverse movement, both this direction as well as in this direction there will be an opposing force. So, this opposing force actually what it would do? It would actually net effect is a force, compressive force acting like this, net effect is at this point compressive force acting like this, compressive force acting like this. So, tension force will be acting normal to the tension force will be acting normal. So, it will act like this and here also it will act like this, no tension will act like this. So, tension acts like this because compression is along this direction, compressive along this direction, net force because of the resultant of the frictional resistance and the applied load. So, net compressive force will be along this direction, which means there is a tensile force, the transverse tensile force because of Poisson's effect will act like this. So, you have a crack in this direction and you have crack in this direction, you have crack in this direction and you have crack in this direction. This is called Platen effect, this is called Platen effect. Okay. Now, supposing I put a material here, I put some material here, I may put some capping material here. Now, machine plate is not in direct contact with the specimen. Machine plate causes the friction is between this and the friction is here now between the machine plate, your load is coming from here and friction is somewhere here. So, this material will try to expand in this manner, but would be resisted by the friction. So, it is Poisson's ratio which causes it to deform along the transverse direction, Poisson's ratio along the transverse direction and its stiffness is an important issue. So, if it moves high, moves quite a bit compared to the stiffness, resistance to movement is stiff, which as a material property for a given force, then for different capping, supposing I have two different capping, their movement along this one, more it moves, it will cause the concrete to move more along this direction. If it is stiff, then the strain, this directional strain itself will be low, therefore, Poisson's effect will be minimal. So, more the Poisson's ratio of this capping material and less the modulus of elasticity of that material, it will tend to actually nullify the Platon effect more. So, in other words, just let me now put it here. Higher nu, where nu is the Poisson's ratio, divided by E, modulus of elasticity, stiffness, more modulus of elasticity, more modulus of elasticity is then less will be the movement. So, nu by E is important. If this is less, this term is going to be higher, and if this is more, this term is going to be higher. So, this if this is higher, so higher nu by E induces higher lateral movement, higher nu by E induces higher lateral movement. So, that is what we have understood, that is what we have understood. I am just erasing it out now, right, again erasing it out. So, softer and weak material has higher expansion, and their lateral expansion is more than that of concrete. So, softer and weak material has higher expansion, and their lateral expansion is more than that of concrete. So, therefore, this will cause, if that moves, concrete will automatically also move, Platon effect will get reduced significantly. Softer and weaker material will reduce. The higher expansion increases lateral move strain in concrete, and crack parallel to the load grows rapidly, leading to failure under lower load. So, you see a higher, so that means if a higher nu by E material as a capping material, that is softer and weak material, you put it as a capping material, it will cause, it will itself expand and will not restrain the expansion of concrete under the Poisson's effect, and therefore, concrete vertical cracks you will see possibly crack parallel to the load, that is downward load. So, crack will be parallel vertical load, vertical cracks, and that would failure will progress under that kind of load. Okay. For strong capping material, result is opposite obviously. So, if the nu by E is small, that means this material itself has low Poisson's ratio and E is high, very stiff, therefore, stronger material has this kind of behavior, and that would actually restrain, and therefore, it would show a higher strength compared to the one with higher value of nu by E, because it will restrain. So, the net effect is the material is not going to expand in the transverse direction, there is a restraint to that. So, net effect is you will require higher load to cause it to now fail. So, this is the effect of end capping, as we have seen. The end platens of the machine produces same effect as strong capping material. So, the capping end platens, machine platens, because steel is a material, it is a strong material, and its Poisson's ratio is divided by modulus of elasticity is relatively low if there is no capping material. Therefore, plate restricts the movement and increases apparent strength, and the degree of restraint depends on friction between plates and the concrete surface. So, that is why everything has to be standardized. You see, you have to standardize your plate, and whether you got to use a capping material or not, that has to be standardized. Normal Q's test, we do not apply any capping material, but wearing this capping material we did understand why possibly a specimen which has got high L by D fails at lower load compared to a specimen which has L by D equals to 1. So, the degree of restraint depends on friction between plates and concrete surface, and for very low restraint capping material, wax, let us say if we put wax, the difference is quite evident from the cracking pattern. We put wax which is a very low restraint, it does not restrain because it is very low strength, weak material expands quite a lot, and therefore, you can find almost vertical cracks, right. Something similar, for example, rubber or Teflon, if you use, it has got a high strength, but low stiffness. So, it allows expansion, but does not fail itself, and therefore, you will find again the effect of the plates are gone. There is something called brush platens, made of plates made of brush, you have brush, closely placed brush platen. So, you use below the plate a brush. So, brush can expand easily, it is a brush, steel brush, you just put that, it can expand, although it will not fail. So, that is it, that is so that is Platon effect basically. So, if you see, if you have no effect, no capping, no restraint practically, and if you have high restraint, then These are the scenario. Low restraint, high restraint. High restraint you will get, because as I told you that net compression, net compression will be along this direction, resultant force. So, transverse tension will act like this, and you have something of this kind. While if you have low restraint, basically wax or something, or Teflon or brush platen effect, brush plate, then cracks would be vertical because of the failure due to Poisson's effect. So, this aspect is to taken into account. So, therefore, we got, if you recall, we got failure of the cube like this. This is the cube failure. If you remember, this is what we showed earlier. In the beginning, cracks will come like this, then this is the shape that you get, and some cases you go further, you might get a shape like this. This is the portion which does not get failed, right. So, this is the final portion. So, platen effect act like this. Due to the platen effect, it is like this, but then restrictive effect is limited up to certain distance from the plate. As I said, it is limited. If this is your specimen, what is important is L by D. So, up to certain portion this is effective. This platen effect, this will act up to certain point, right. It will act up to certain point, does not act full length. So, this act up to certain point, right. This act up to certain point. Okay. So, in this direction also it will be there. So, it will act like this. Now, how much is this distance? This distance is seen to be, it is related to this d, this can be related to this d. So, it has been observed that up to about 3 by 2, 3 by 2 maybe H6 d, 3 by 2 d, up to this d, the end of the cylinder diameter thus. So, it is actually estimated actually up to 8.6 d, this effect will be there. So, if this is d, 0.86 d, this distance will be 0.86 d, sorry 86 d, 0.86 d, this side also 0.86 d, this side also 0.86 d. So, you have L equals to d, which is the case for cube, actually there is an overlap of the platen effect, because this is 0.5 d and this side 0.5 d. So, it goes up to 0.86 d. So, platen effect, practically this effect of restraining effect of the plates works over the whole of the specimen. But if you have a cylinder with h by d is equals to 2, h by d equals to 2 for cylinder. So, in that case what is happening?